chapter 3. Chapter 3 and 4 are both on exam 2. And we're going to talk about stoichiometry. I noticed some of you had trouble naming compounds in that exam. That you need to fix that. And I mean in a hurry, because we're going to get heavy into naming compounds, writing equations, and you need to know how to do that. If you don't, make that your highest priority. So what is stoichiometry? Well, rather than go into the etymology of this word, let's just say it's a way of budgeting materials that go into a reaction and come out of a reaction, and based loosely upon Lavoisier's work, conservation of mass in a reaction. But we're going to learn how to write a chemical sentence, which is an equation, and track where the reactants are going during the reaction, and determine what the products, how much of the products come out of the reaction. But obviously we need a little background first. So the problem with doing chemistry on this level is that we can't track individual atoms and molecules. Right? They're too small and too many of them. So we have to devise a way to, on the macroscopic level, to get a handle on how much is going in and how much is coming out. And that's where this concept of counting by weighing occurs. And it's a way of approximating the number of things, atoms, molecules, whatever the case may be, based upon the weight of those items that we know are in the process, in the chemical reaction. So we weigh them, we don't count them, but we infer the numbers based upon their weights. And by that, of course, I mean the mass. All right, so here's how we do it. First of all, well, I already said that atoms are too small to count. We do have to assume that all the objects that we're counting behave as though they were all identical in terms of the mass per individual item. And then we also, in order to get a handle on this, we need to know the average mass of the object. In other words, if we have a billion sulfur atoms, we can't count that many, but if we can weigh the sulfur atoms and we know how much each one weighs, then we can infer how many there are. It's a dimensional analysis problem. And I'm getting there. Okay. So let's take, for our example, this pile of marbles. Then we have a pile of marbles that weighs 394.8 grams. So we got marbles in here, right? It's full of marbles. And they weigh 394.80 grams total. We want to know how many marbles are in that container, but we don't want to count all. So what we do is we take 10 of them out. We take 10 of those marbles, 10 marbles, and we weigh them. And we get 37.60 grams per 10. So we know that the average mass of a marble is 3.760 grams per marble. Okay? Now, if we know that's the mass of each marble, this is a conversion factor. Remember? Each marble is equivalent to 3.760 grams. So we could take this and do our unit conversion, just like we've done in the past, and convert grams to marbles. If we just need grams, goes on the bottom, 3.760 grams per marble. Divide that into that, and that tells us, because these cancel, that tells us how many marbles we have. So that's the concept behind counting by weighing. And it turns out we have 105 marbles in here. Now, obviously, we know with any measurement, we get what? Uncertainty. So by this calculation, all this work we've done, we calculate that there are 105 marbles in there. Maybe they're not. Maybe they're 106, maybe they're 104. But that's the trade-off. We have to live with the uncertainty. What we do is we try to minimize the uncertainty. Maybe what we'll do next is put those 10 marbles back and take out 10 others and weigh them and do the same thing and do that 3 or 4 times. Then we get a better estimate of, we narrow the precision. Okay. It's called replication. So now the question becomes, how do we count the number of atoms in a pile when the atoms are too small to weigh? That was the monster problem for scientists up until about the middle of the 19th century. Right? They could weigh things, sure, but they didn't know what they were weighing. They thought they were weighing the right numbers, right? But they didn't have a concept. They really didn't know how to get a handle on how many particles were in the container. You need to know that, or you need to know how many particles weigh that amount before you can use this counting by weighing. And that's where Avogadro came in. Remember his law? Nobody remembers Avogadro's law? 2 gases in equal size spheres. Yeah, they have the same number of particles if temperature is the same, pressure is the same, volume is the same, then they have the same number of particles, right? That's how they got a handle on relating the number of particles, the number of atoms, the number of molecules in a container. So then what you had to do was settle on a mass for one of them, and then the rest of them you could relate to that one. Okay. Did we cover that yet? We didn't cover that yet. Okay, good. Okay, so that's what we're going to do. We're going to pick a standard mass for one of the isotopes of an element, and that's going to be our reference point. And as a matter of fact, well, let me see, I probably got it in a slide, so I don't need to steal my own thunder. We use carbon-12 as our standard. That isotope of carbon, right, with a mass number of 12, which means it has 6 protons and 6 neutrons. That's our standard. And this is set, this is an atom. That atom has a mass of 12 infinite atomic mass units. Okay, and everything else is referenced to that. We use carbon now because it's very easy to obtain. Right? Carbon's everywhere. All you have to do is ash your sample, separate the carbon from the ash, then run it through a mass spectrometer, and you can separate this isotope. And it's fairly abundant for carbon isotopes. It's the most common one. Okay, just historical reference. They used to use oxygen. They started off using oxygen because all the metals on the planet are in some form combined with oxygen. So they figured, well, oxygen's pretty common. But it turns out oxygen is not easy to handle, right? Because when you get pure oxygen, you got a gas, and that presents problems. But with pure carbon, you got a solid, and it's easier to handle. Okay, now your authors use the letter U for atomic mass units. I prefer AMU because then I don't get confused with some other, like the Greek symbol for micro. It might be easy to confuse with that one, so I use AMU. All right. So since elements occur in nature as a mixture of isotopes, we assign masses based upon this reference, assign masses to all the other isotopes, including carbon-13, which is the next most common isotope of carbon, but it's not going to be 13 atomic mass units because we're referencing it to this. It's going to be a little bit different. And the rest of the elements they're all different. They're fractional. In other words, they're not whole numbers. When we learned this as the mass number, we were saying that's the summation of the protons and neutrons. This is the only one where the mass number equals the atomic mass of that isotope. Right? So there's a difference. This is the mass number, and this is the atomic mass. So the atomic mass of every other element is a fraction. It's something point something something something. That being said, you also introduce the concept of weighted average, right? When you take a sample of any element from nature, it's going to be a mix of isotopes, right? So you can reference the isotopes to this standard, but even then, you've got to take the percentage weight of each isotope for the elements. Most of them are one isotope is the lion's share, it's the dominant one. There are only a couple of cases where you get roughly equal amounts. Chlorine's one of them. And that's why chlorine, when you look at your periodic table, you see these values here, right? And they're always point so many decimals. That's because they're weighted averages. Right? Everybody knows how to do your grade point average, right? Yeah. You're weighting the value of the grade in this class based upon how many credits it brings. So 3 credits in this class, an A at 3 credits in this class is worth a whole lot more than an A 1 credit in the lab. And that's the way we do elements. When we determine the average atomic mass for an element, we do a weighted average of all the isotopes. And that's great for us as chemists because we don't have to deal with the isotopes, right? When we take a sample from nature, the percentage composition of the isotopes has already been factored in to that value, right? So we don't have to have a mass spectrometer in our lab to do chemistry. Okay, now this carbon-12 happens to be over 98%, almost 99% of the naturally occurring isotopes of carbon. And carbon-13 is a little over 1%. So if we use that information to calculate the average atomic mass, well, we actually need a value for the carbon-13 because we can't assume that it's 13 unless we just force it to be so that we can do the calculation. But carbon-14 is insignificant, right? Does anybody know why carbon-14 doesn't matter that much? Well, 2 reasons. And they're related, right? See, 0.01%, right? What impact would that have on the overall average? Not much. But why is it so low? Because carbon-14 is radioactive, right? It doesn't hang around for very long. And pretty soon it's gone. Well, actually, we're making more of it all the time because other isotopes of carbon are exposed. Actually, I think it's nitrogen in the upper atmosphere gets exposed to ultraviolet radiation, and that causes a transmutation to carbon-14. So there's a level of carbon-14 that's pretty consistent, but it's also disappearing at the same rate. But since it's such a small amount, we're not going to use it for the calculation. Here we have 98.89% of 12 atomic mass units and 1.11% of 13.0034 atomic mass units. Right? So that carbon-13, which has 6 protons, right, because it's carbon, and 7 neutrons. But its mass, its actual mass is more than 13. And that actually makes sense. If you think that protons are 1 unit, neutrons are a little bit heavier. Anyway, so how do we do the weighted average? Well, you can't use percent because percent's a dimensionless number. It's parts per hundred, right? You could use it, right? But you still have to write it 98.89 divided by 100 times the value. So what I do is just go ahead and divide that 100 into it and use the fraction, 0.9889 times 12. That's the contribution to the average atomic mass of the carbon-12 isotope. And 0.0111 is the decimal equivalent of 1.11% times 13.0034. And that's its contribution to the total in the natural mix of carbon-12 and carbon-13. And then when you multiply those out and you add those together, you get 12.01. And that's the value we generally use for carbon in this class when you're doing a calculation later, right? And that's coming also. Okay. So the takeaway here is not just that 12.01 is the weighted average of carbon, naturally occurring carbon with its carbon-12 and carbon-13 isotopes. Understand that if you find an atom, if you were able to isolate one atom from a mix, a natural mix of carbon, then the question is, will it have the mass 12.01? No, it won't. That's a calculated value, right? Each atom has its own atomic mass, right? The carbon-12s will be 12, carbon-13s will be 13.0033. Right, so 12.01 doesn't represent the exact mass of any single atom. Okay, but it's just as useful because now we don't have to separate the isotopes to get a handle on the mass of one atom. It's a weighted average. Okay, so this is just a representation of a mass spectrometer. And I'm not going to spend a lot of time on it, just to say that if you want to separate isotopes of an element, you need to take advantage of their differences. Chemically, they're the same, right? So you can't separate them chemically, but each one has a different mass, right? The 12s have their mass, and the 13s have their mass, 14s have their mass, and there are several others that are even smaller percentage. What you do is you fire your sample through an ionizing chamber, and it strips the electrons off of them, makes them positive ions. And then you accelerate them through an electric field. That's what those first two are. Let's see, right here. There's your electric field, and you take those positive ions and you accelerate them through this electric field, and then you send them through a magnetic field. And the magnetic field will cause them to curve, right? The magnetic effect on a moving electric charge is that it curves. So the ones that curve the most are the lightest, right? Because they weigh less, right? They've all got the same energy because they went through the same electric field, but their mass means that the influence of the magnetic force upon them is less if they're heavier. Does that make sense? Okay, so the heavy ones are going to be in this example, in this artist rendition, the heavy ones are going to be out here, and the lighter ones are going to be here. And if your instrument is properly calibrated, you can actually count the number of atoms, right? The electronics are fast enough now that they'll count individual strikes on the detector. And that way you can associate the mass with its relative abundance, those percentage values. That's where they come from. Now this is an example. And this was an original. This is called a magnetic sector mass spectrometer. There are other types now. Quadrupoles are a lot cheaper to make, and typically what manufacturers use to produce them, but they have the same effect. Okay, so let's take this example. An element consists of 62.6% of an isotope. 62.6% of an isotope of an element, which has a mass of 186.956 atomic mass units. Okay. Another isotope has 37.4%. 37.4% at a different mass, more than likely, 184,953. The question is, what's the average atomic mass and what's the element? Okay, let's convert this to a fraction. 0.3740 and 0.6260. And we'll take that, this one times that one, and this one times this one. And we get a couple of values. And then you add them together. Because what we're doing here is we're assigning what's the weighted contribution of that isotope, the weighted contribution of that isotope. Then we have to add them together to get the total weighted average. Okay, so 186.956 times 0.626. Okay, this is 117.03035. And this is 172. Okay, so we add those together. That's a 7, 10 to 16. 186.207 atomic mass units is the weighted average for that mix of isotopes. All right, so how do we use that value to find out what it is? Let's see. Did we get that right first? Yeah, close enough. Okay. So how do we figure out what element it is? We don't know the number of protons. The periodic table is arranged by increasing atomic number. You can see that here in the reds. But also, along with that, the atomic mass increases. That's what these values are. Okay? For our purposes right now, these represent the weighted average of all the naturally occurring isotopes for this element. And we can look for that value in here. There are only a couple of places where the weights are swapped, that they're not in order. Mendeleev, when he put the periodic table together, recognized that. And he says, okay, remember that discussion? Right? If they had in the group, he was looking for similar physical and chemical characteristics. Right? If he put one in here based upon its weight, and they didn't know about Mendeleev's day, they didn't know about atomic numbers. He was ordering things by weight until he found one that didn't fit in that group. But the one behind it maybe did, or the one ahead of it, and he swapped them to make them fit. So back to this 186.2. All right, we just follow it along. 186.2. That's rhenium. Usually, the weighted average masses are different, or sufficiently different, so that you can use this also to find the element. Question? No? I thought you were pointing with your pencil.
No, I'm sorry.
They're like I say, there are only a couple of places in there where the masses are so close together that experimental error might overlap, right? So then you have to use either guess or use some other method to break the tie. But most of the time, and at least for this class, right, when you're looking for one of those, you can find the element if you know the mass. Okay? That's not one I told you to memorize. It just, that answers this question though. Okay. Now, if we weigh an element, if we get its mass in the lab, and it's in the grams range, atoms are so small, you're going to have billions and billions of those things. So we need a more convenient unit of measure for counting atoms, and that's what the mole is. The mole is actually a number. I may have shown you this before. 1 mole, and that's the whole number. And oddly enough, that's the abbreviation. Is 6.022 times 10 to the 23rd. For our purposes, atoms, but it could be anything: molecules, ions, chicken, whatever. A mole is a mole. A mole is that many things. So it's a very, very large number. And by definition, this number is the number of carbon atoms in exactly 12 grams of pure carbon-12 isotope. Okay, so what that means is, cut to the chase. If you have a mole of any one of the atoms, say, even if it's a mix of isotopes, naturally occurring element, if you have a mole of them, then they will weigh that many grams. Okay, so that value represents an average atomic mass in atomic mass units for one atom, or the average atomic mass for a mole of those atoms in grams. Now that's something we can work with because our balances are calibrated in grams. Okay, and that's Avogadro's number. Now Avogadro didn't come up with it. This is an honorary thing. His Avogadro's hypothesis is what allowed us to derive this number. Okay, so we give him credit and name the number after it. And the number, I'm sorry.
Do you know who actually named the number?
I can't think of it right offhand, but I'm sure the information's out there. Okay, and this number is refined periodically to more decimal places than we're using here, but I've never seen it change from 6.022. It might change in about the 6th or the 7th decimal, right? But that doesn't affect us. Okay, so 1 mole of carbon, naturally occurring carbon, is going to be 12.01 grams. Now you've got more decimal places here, but when I submit problems to you, you only need 2 decimal places in that value. So if your periodic table goes out 4, just round it off to the 2. Okay. If you want your answer to come close to mine. Okay. Now we can calculate. Now that we have our standard carbon-12, and we know how many atoms there are in a carbon-12 isotope to make up a mole. Now we have a point of reference and we can expand into other elements. So iron atoms that are 4.48 moles of iron, if you have that many iron atoms, how many numbers of iron atoms do you have? Well, now we're back to dimensional analysis, right? Conversion factors. Remember, we had an equivalence. 1 mole equals so many atoms. Whenever you have an equivalence, you also have a conversion factor. So here we have moles on the bottom. Right? 1 mole is how many? 6.022 times 10 to the 23rd atoms. So moles cancel, and we convert to this many moles of iron, we convert to a certain number of atoms. Right? And there you are. 2.70 times 10 to the 24th iron atoms. Now this is an exact number for conversion factor purposes, right? So we're only limited to 3. That's why 2.70 is the number of significant figures. All right. So this is what we call the molar mass, this value. If we're speaking in terms of grams per mole, obviously it's molar mass. Sometimes I slip and say atomic weight, right? But I mean molar mass. And you can get that from the periodic table, right? Nitrogen is 14.00672. Rounded off the 2 decimal places is 14.01. Now that we know the molar mass of individual elements, we can calculate the molar mass of compounds, right? How much does a mole of a compound weigh? And our example here is water, right? The way you do that is you recognize that if you have 1 mole of water, how many moles of oxygen do you have? You have 1 mole of oxygen, right? Because there's only 1 per 1. But you also have 2 moles of hydrogen in that molecule. Okay? Nobody's arguing. Are you just stunned? If you have 1 mole of that compound, it has to be made up of 1 mole of oxygen and 2 moles of hydrogen. Okay? So now that we know that, we can say, all right, if 1 mole of oxygen weighs 16 grams per mole, right? Moles cancel. 16 grams. This one is 1.01 grams per mole. Right, so that's 2.02. So 2.02 plus that one is 18.02. So 1 mole of this is 18.02 grams. And that's how you calculate the molar mass of a compound. You use the formula. Right? We could do it with something really complicated, like, I don't know, ammonium phosphate, right? We need 3 of these and 1 of those. And so all you need to do is say, all right, how many nitrogens do you have? 3. 3 nitrogens. How many hydrogens do you have? 12. How many phosphorus do you have? 1. Oxygens, you have 4. So you multiply this one times the nitrogen value, 12 times the hydrogen, 1 times the phosphorus, and 4 times the oxygen, add them together. And that's how much a mole of that will weigh. Okay, I think I've got an example. Come on. Let's see. And we're going to use barium nitrate, right? Similar concept, right? You got 1 barium. That's this one right here. That's 1 barium. This is 2 nitrogens because you've got nitrate in the parentheses and a subscript of 2. So you have 2 nitrogens. You have 6 oxygens. 2 times 3 is 6. Add them all together, and that's what barium nitrate weighs per mole. Okay. All right, we're getting there. This is essential. Understand this is essential in order for us to track the changes in mass of reactants to products. Now, the other thing we need is a balanced equation. We'll get there. Which of the following is closest to the average mass of one atom of copper? I don't know why I keep this slide up here. It's kind of stupid, right? One copper atom, can it weigh 63.55 grams? No, right? It's got to be E. And you can calculate that. Like the average mass of one atom of copper. Let's see. Did we do the calculation? Yeah, there it is. So it's a chained conversion. You have one copper atom and 1 mole of copper is 6.022 times 10 to the 23rd copper atoms. So that cancels the atoms. Let's see. Did I animate that one? Yeah. So we cancel the atoms. That leaves us with what? Moles of copper. And now our relationship between moles and mass is right off the periodic table. 63.55 grams of copper per mole. And that cancels the moles and leaves us with grams. Right? And that's E, that value. Okay? Chain conversions. All right, this is a trick question. Calculate the number of copper atoms in 63.55 grams of copper. Right. 1 mole, 6.022 times 10 to the 23rd. All right. Now we're getting a little deeper into the weeds. Which of the following 100-gram samples contains the greatest number of atoms? So we've got magnesium, zinc, and silver. Magnesium, zinc, and silver. And each one is 100 grams. Okay? We want to put them in order of greatest number of atoms to least. Oh, actually, we want to find out which one's the greatest number. Okay. So, think of it this way. If you have a bunch of bowling balls over here, and you have a bunch of wiffle balls over here, and you need the same mass of each one, which one's going to take the most number? Yeah, because they're the lightest. And same concept with elements, atoms. The one that has the most number of atoms is going to be the smallest one, the one that weighs the least. So all we have to do is look up the values. Magnesium is 24.31 grams per mole. Zinc is, well, we just did that one. 60, no, we didn't. We did copper. 65.38 grams per mole. That one's pretty close to copper. No, it's a couple of grams off. And silver, 107.87 grams per mole. So, 100 grams of magnesium is going to have more atoms because it's the lightest. That's the concept here. Now, if we put them in order, right? Greatest to least, this would be the great. This would be the greatest. This would be the next. And this would be the least number, because it comes in inverse order to the atomic mass, the molar mass. Okay. All right. So let's see. We have silver. We have 107.9 grams. We're given that mass, 107.9 grams. Zinc, we're given 70 grams. So we don't have 100 grams anymore. We've got a specific mass for each one. And then magnesium is 21 grams. All right. Now what we want to do is order them greatest to least. When you have just 3 to choose from, you want to put them in order, the simplest thing to do is to say, all right, do we have a mole? Do we have less than a mole or more than a mole? Right. In this one, we have less than a mole, right? That is less than 1 mole. How about this one? That's greater than a mole, right? And this one is exactly 1 mole. Now we can put them in order from greatest to least. All right. This is greater than a mole. So zinc comes first. And then 1 mole, silver comes next. And then magnesium comes last. In terms of number of atoms, moles of atoms. Did I lose anybody? Yeah. Okay. I get that one animated. Sometimes I forget they're animated, so I go ahead and put it on the board. Okay. Now, if the weeds are getting thicker, we have these 100-gram samples of these compounds. We have water, dinitrogen monoxide, which is, it's often called nitrous oxide. Everybody ever had a tooth pulled? It's laughing gas. That's what you were breathing. C3H6O2, C3H6O2, I think that's propionic acid. And then carbon dioxide, right? 3, 4, okay. So we have 100 grams of each one of these. Now, the reason I've got that statement at the bottom, time for Henry Ford. What was Henry Ford famous for? The assembly line, right? We're going to set up an assembly line. We're going to do each one of these exactly the same way. Only we're actually better than Henry Ford because he said you could have any color you want as long as it was black. He really did say that. What about the Model T? But we've got different colors. So we have different values here. We want to convert this to greatest to least number of oxygen atoms. Okay. In order to do that, we got to find out how many atoms of the molecules we have. Then we can apply the ratio of atoms to moles of the molecule. Everybody see where I'm going here? Okay. So we want to convert this to numbers, and we don't have to go down to individual atoms, actually. We just need to go to moles, because moles is a counting unit also. So this one, we're going to convert grams to moles of the molecule. Remember 18.02? We're going to do the same thing for this one, only it's going to take a different value. 1 mole on top, how many grams on the bottom? Well, 14.01 times 2 is the nitrogen, plus 16. Okay. So that's 2802 or 4402 grams per mole for nitrous oxide. And propionic acid, that takes a little more. Let's see, 3 times 12.01 for carbon, and this is grams per mole. Hydrogen, 6 times 1.01 for hydrogen, and 2 times 16 for oxygen. And we have to add those together. So let's see, 12.01 times 3 is 36.03, and then 6.06 for hydrogen, and then 32 for oxygen. Right, 2 times 16 is still 32, I think. 7409. 74.09 grams. Oops. There we go. All right, and the last one is carbon dioxide. 2 oxygens is 32, and then 12.01 for 1 carbon is 4401. Okay, so that'll give us the number of moles of the compound for 100 grams. Okay. So we cancel the grams, grams. This is moles of compound. What we want is moles of oxygen. So I'm going to chain them together. So for 1 mole of compound, how many moles of oxygen do you have? 1 mole of oxygen. Right, 1 to 1. One of these for every one of those. Okay, that's the conversion factor. How about this one? Same thing, right? How about this one? This one has 2 moles of oxygen for every 1 mole of compound. And this one also 2 to 1. Okay, so that cancels these moles of compound, that, and leaves us with moles of oxygen. That's the thinking part. The rest is number crunching. So let's see, 100 divided by 18.02 times 1 is 5.549. I haven't rounded it up yet. This is moles of oxygen in 100 grams of that sample. And 100 divided by 44.02 times 1 is 2.2717. 2.17, let's round it off to 2 moles of oxygen. This one is 100 divided by 74.09 times 2 is 2.699 moles of oxygen. And the last one, 100 divided by 4.01 times 2 is 4.544. 4. Okay. Greatest to least. So this is the greatest. This is next. This is next. This one is last. Okay. That's what I mean by Henry Ford. Those the calculations were the same. We just changed the relevant numbers. Okay. Let me see if I got them right. The greatest to least. Yeah, greatest. There we go. Greatest, and then carbon dioxide is 2. Yep. And then propionic acid, and then nitrous oxide. All right. We've seen this slide before, haven't we? Problem solving. Yeah. Where are we going? I like to think of it in these terms. What's the question? What question are you trying to answer? Then how are you going to get there? Right? What materials, what information are you given in the problem? Do you need to go out and get other information like from the periodic table or from your useful information page, that type of stuff? What do you need? And work the problem through. Sometimes it's really simple calculations. Sometimes it's a chain conversion, which is pretty simple. Sometimes you have to break it into pieces and then bring the answers to those pieces together. I think we did one of those. Maybe. I get confused between this class and my other classes. And then you go back and say, does the answer make sense? Well, I can't say that any one of these makes sense intuitively, right? And estimating them is probably not going to help me much, but whenever you can, if you can run a mental estimate of what the answer should be, at least to orders of magnitude, right? How close should it be? And then, you know, if your answer is supposed to be 10 to the minus third, and you get 10 to the third as your estimate, then you probably want to back up and check your math again. All right. Mass percent of an element. What we're getting at here is when you have a compound and you're a bench chemist, say, right? That's what you do all day long. You just do analyses. One way to express the composition of a compound is percent by mass. Right? So you would have grams of some element in grams of the compound times 100. That would be mass percent. Okay, that's what that thing means right there. This is very useful. I mean, it's convenient for the bench chemist, but it's even useful for us if we want to calculate the composition or come up with a formula for the compound. Okay? But remember, the formulas for compounds are not based upon mass, they're based upon numbers of atoms. So I got to show you how to get from one to the other. Well, first we're going to work it from this direction. Say you already know the formula, Fe2O3, for example. Calculate the percent by mass. Well, since this is a dimensionless number, I mean, look, grams cancel. Right? There are no dimensions there. Unless you know what it's derived from, then you can work backwards. But if we say the formula is Fe2O3, how do you calculate the mass percent of that? Well, you have to make an assumption. Let's assume that we have 1 mole for that compound. Now we got something to work with. If we have 1 mole of that compound, what's the total mass? Right? Fe2O3. All right. So let's look up here, find iron, 55, 84, 52. Times 2, right? Well, I broke my own rule. There we go. Let's do that. Let me back up. It's about 85. Yeah. Okay. Enter 2 times that. So that's 111.70. That's the contribution of iron to 1 mole. This many grams. How about 3 oxygens? Oxygen 16, so 3 times 16 is 48. Right, so we had 48. 159.70 grams per mole of compound. Okay. Well, if we want to know, let's see, for iron, we want to know the percentage by mass of iron in this compound. We already calculated how much iron is there, 111.70 grams of iron per mole of compound. Right, so these cancel. And we have grams of iron per grams total times 100. And that's percent of our iron. 111.7. So I get, let's see, 4 significant figures. 7.3. That's not right. We do that again. See, I just did a fast calculation in my head and said, the answer I got here can't be right. So let me back up and do it again. 111.7 divided by 159.7 times 100. That's more like it. Now I get 69.94% iron in that compound. Okay? That's how you do it. If you know the formula for the compound, you can calculate the percent. The next thing I want to do, I think it's coming up next, is show you how to get to Fe2O3 if you know the percent by composition of the elements. That's more important, actually. We're not going to do that right now. Looks like the next slide is taking us in a different direction temporarily. Let me see, am I gonna have time to finish this? I need to step on it. All right, 100-gram samples of the following, rank them from the highest to the lowest percent oxygen by mass. Oh, okay. So I'm just going to take one example. Water. You have 100 grams by mass, right? 100-gram sample. Remember what percent means? Parts per hundred. Almost shut down on me again. Guys, forgot to plug it in. Percent means parts per hundred. And here we have 100. So all we need is how many grams are in 100 grams of that? How many grams of oxygen are in 100 grams? Okay. Actually, that's the hard way to do it. If we're only looking for percent, then we can do it the old-fashioned way, right? How much does a mole of this weigh? Well, a mole of that weighs 18.02, right? Grams. How much of that is oxygen? Well, 16, right? One of them times 100. Math's not telling us. All right. So that's the way you would do the whole thing. Actually, the 100 grams is it's like blue smoke. Okay. It doesn't matter whether you have 100 grams or not, because it's asking you for the percent of oxygen by mass in each one and order them. Right, so 16 divided by 18.02 times 100 is 88.79. You do that same thing for each one of them. Right? Carbon dioxide is 12.01 plus 32. And that goes in the denominator. What goes in the numerator? 2 times 16, 32. Okay. Times 100. You just do each one of those calculations and you get that order. All right. Oh, good. Now we're going to use percent composition to determine the formula of the compound. But it's a little more complicated than just than going from the compound formula to percent by mass. In this case, what we're going to get with the percent by mass is an empirical formula, not the molecular formula. The empirical formula is the simplest whole number ratio of elements in the compound. All right. So, for example, if I write this one, which is benzene, or I write this one, which is acetylene, right? They both have the same empirical formula because the ratio is 1 to 1 for both of them. Right? Their empirical formula would be CH. We can calculate that from percent composition. In fact, percent composition is the same for each one of these. In order to go from percent composition to the molecular formula, we need another piece of information. And I'll call your attention to it when we get there. But we need to do empirical formula first. I'm not going to spend a lot of time here. This is a carbon-hydrogen train. You combust your sample in a furnace and you blow pure oxygen through it. And this is particularly useful for carbon-based compounds. The carbons are all converted to carbon dioxide, and they're absorbed in in this material, right? Let's see. Here. They're absorbed in this material, right, such as magnesium perchlorate. And then the water passes on through that. Actually, magnesium perchlorate is not a good choice. I would say sodium hydroxide or potassium hydroxide would be better, because magnesium perchlorate will absorb water. Oh, excuse me. That's what it does first. I've got it backwards. Hydrogen, water first, and then carbon dioxide in sodium hydroxide. Okay, that's better. And then you know the total mass of your sample. So if you know that carbon, hydrogen, and oxygen are the only elements in there, you can get the oxygen by difference. Get that out of the way. All right, we're not going to spend a lot of time on that one. So let's use this as an example. First, we're going to get the empirical formula, and we're going to use Henry Ford again. 49.3% carbon, 49.3% carbon, 6.9% hydrogen. Okay, and oxygen, 43.8%. Now, let's see, that should add up to 100%. Now, how do we get percent composition by mass out of this? Well, like I said, this is, percent is a dimensionless number, right? In order to go to moles, which is where we're headed, because in order to get an empirical formula, we have to know the relative moles of each element in the compound, or the relative atoms, which is essentially the same. So we have to make an assumption, right? We got to get some mass out of this before we can convert it to moles. Assume that your sample is 100 grams. Okay? If your sample is 100 grams, how many grams of carbon do you have? Right? 49.3% is 49.3 grams per 100 grams. So if you assume a 100 gram sample, that's how many grams of carbon you have. And the ratio is fixed. This amount is fixed. Remember the law of definite proportions, right? That proportion is fixed. So we can change it and still get the same ratio depending on our mass that has no influence on it, on the percent. So when we say we have 100 grams, now we have 6.9 grams of hydrogen and 43.8 grams of oxygen. Oh, we don't need that. All right, now we can convert to moles. Grams, grams, grams. Mole. Mole. Okay. How many grams is carbon in a mole? How soon we forget? 12.01. And if you forget, just look it up in the periodic table. 12.01078. Round it off. How about hydrogen? 1.01. And oxygen is 16. Why can I round it to that? Because oxygen is 15.99943. Round it off to 16 in two places. Okay? All right. So if we divide, we're going to do this in several steps. 49.3, and we divide 12.01 into that, we get 4.105. 4.105 moles of carbon. And 6.9 divided by 1.01, we get 6.83. 6.832. Yeah, I'm just checking my math. Estimating. 43.8 divided by 16 is 2.738. And notice I'm adding decimals there, right? We're limited to 3 figures here, 2 there, and 3 there. But that won't matter until the end because we're doing all adds We're doing all multiply divide. Okay, that doesn't look like a whole number ratio, does it? How do you get a whole number ratio out of that? The simplest way is to take the smallest one and divide that number into everything. Right? The ratio is fixed. This is the number of moles of carbon, moles of hydrogen, moles of oxygen in a 100-gram sample. Now that we've got the ratio, we can shift the ratio any way we want, as long as we do the same thing to each one. So for this one, we're going to divide by 2.738. We're going to divide this one by 2.738. This one by 2.7. Right, this is 1, obviously. Let's see. Divide by that. 2.496. 2.496 and 4.105 divided by 2.738. And this is 1.499. Now we're at the point where we need to get close to whole numbers. This is about 1.5, right? Very close to 1.5. This is very close to 2.5, and that's 1. So now what do we need to do to make all whole numbers? Multiply everything through by 2. If we multiply this times 2, we get 2, times 2, we get 5, times 2, we get 3. So the empirical formula for this compound is C3H5O2. Okay, that's the simplest whole number ratio. That's not the molecular formula. This is the empirical formula. It could be that if we multiply by 1, it could be that if we multiply by 2, it'll be 6, 10, and 4. If we multiply by 3, remember the multiplier gives us the molecular formula. Remember when we had this one? C6H6. That would be equal to the empirical formula times 6 as a multiplier. Right? 6 times that one, 6 times that one would give us this formula, correct? Okay, so if we think of that in these terms, we have a multiplier here. What is that multiplier? Well, in order to go to the next step, we need to know what is the true molar mass for that compound. The mass for a mole of that compound. The easiest way to do it is to calculate what is the empirical weight for this compound, right? 3 times carbon, 12.01, 3 times, 36.03, 5.05 for hydrogen, right? 5 times 1.01, add that together, and 2 times 16 is 32 for oxygen. The empirical mass is 364.0 grams per mole of that formula. Did I do that right? I better check myself. 12.01. I think I did something wrong. 3 times. I did do something wrong. Okay. That just didn't look right at all. 73.08 grams per mole of that compound. So the true molar mass is going to be some multiple of this, right? That value multiplied by this one will give you the true molar mass for the compound. Because if this is 1 times that, 1, 3, 5, and 2, it'll be that value. If this is 2, it'll be twice that value, right? You don't look convinced. Well, the value that's given is 146.146 grams per mole. So 2 times this is equal to that. Right? So X equals 2, and our molecular formula is C6H10 0.04. Okay. Did I lose anybody? I lose the whole class.
How did you get the 73.8?
I did 3 times 12.01 plus 5 times 1.01 for hydrogen plus 2 times 16 for oxygen. Okay, that's the what I call the empirical mass. It's the mass of that unit. Only we actually need 2 of those units. So if you calculate the molar mass of this one using that method, you get that value. Okay. So in order to go from percent composition to molecular equation, we need the percent composition, but we also need to know by some other method the molar mass of the compound itself. And we're not explaining how we get that. There are several ways to do it, depending on what the nature of the compound. There are a number of ways to do that. But we may not get to some of them until next semester. All right. So I'm over time. They're probably going to cut me off any minute. Let's see. What we need to go from there to stoichiometry is the balanced equation. I'm going to try. I'm just going to keep going and see if they cut me off. See, maybe they won't. I can always go back and.
I have a question. Are you going to be in the same room or are you moving rooms?
I'm going to stay here until they cut me off. And then we're going into the lab.
Okay, I will be there in just a few minutes.
Okay. So chemical equations have by convention, the reactants are on the left-hand side with plus signs in between the various compounds and elements and an arrow, and then the products on the right-hand side, however many it takes, with plus signs between the compounds. And then to say how many of each molecule or atom or whatever the case may be, you need coefficients. That's what that 3 in front of the O2 means, the 2 in front of the CO2 and the 3 in front of the water. That means you have that many. You can think of it 2 ways. Either it's 1 molecule of ethanol, C2H5OH, plus 3 molecules of oxygen yields 2 molecules of carbon dioxide and 3 molecules of water. Or it also means 1 mole of ethanol plus 3 moles of oxygen yields 2 moles of carbon dioxide plus 3 moles of water. Either way works. The most useful way to think of it is in terms of moles. But it's always numbers of things. And that just tells you what I just told you. These ratios, the coefficients, and if you don't have a coefficient in front of the compound, it's automatically 1. Because if you've got it written there, there's got to be at least 1 of them. So we're not redundant with that. If there's 2, you put a 2. If there's only 1, you don't put a number. Okay. And remember that when we're counting things up later, don't forget to count that 1. This balanced equation is the theoretical process. In other words, when we get that ethanol and oxygen together, theoretically, it'll produce that many numbers of carbon dioxide and water. Right? We're going to talk about efficiency later. We have to assume at this point that it's 100%. But I'm just giving you a heads up. For practical purposes, it's never 100%. Okay, these are steps for balancing an equation. I'm going to skip through there just to say that your book probably says balance by inspection. Once you write the compounds in their proper position, right, and that's where you have to know how to write them from their names. If you can't do that, then you're stuck. Can't go any further. But when they say balance by inspection, they're copping out. They're not telling you how to do it. So that's what this handout was for. Balancing chemical equations. These are helpful hints. These are not step by step, but they're helpful hints on the way. And what I'm going to show you first is my budget method. Okay, and they're the helpful hints, one after another. All right, so rather than use this complicated one first, let me take a simpler one. Actually, let's take the example that was given earlier, right? C2H5OH. The reason it's written this way with the H's here and here is because this H is attached to that oxygen, and this oxygen is attached to that carbon, or one of those carbons. Okay, it's written that way for that purpose. Then we have oxygen, right? Diatomic. You better write it that way or it won't balance. And then you have water as a product and carbon dioxide as a product. Okay, the budget method simply says first, you write the compounds correctly or the elements correctly, whatever the case. And then you do an assessment. What's on this side and what's on that side? The elements that you have. On this side, you've got carbon, you've got hydrogens, and you got oxygens. That's it. Carbons, hydrogens, oxygen. We've accounted for all our elements. Now, how many are we starting with? Well, 2 carbons here, 5, 6 hydrogens, 1, 2, 3 oxygens. On this side, we're starting with 1 carbon, hydrogens 2, and oxygens 3. Okay? So now you have to decide where to start. The only way that you can balance an equation is with coefficients. You put numbers in front of the compounds and elements. Once you've written the compounds or elements, you cannot touch the subscripts. Touching the subscripts, changing them in any way is cheating. Okay, so if we've got 2 carbons here, if you don't know where to start, you don't have a good place to start. First thing you want to do, and it's in the helpful hints, is if you've got an element on one side or the other, leave it alone till last. Any idea why? Because when you put a coefficient in front of this one, you're only changing that one. You're not messing with the others like you would be with this one or that one or that one. So save these till last. And then if you don't know where to start, then I always just start at the top. You'll eventually get there. All right, so we need 2 carbons on this side, don't we? All right, so we need 2 here. That gives us 2 carbons, correct? How does that change the others? Well, it makes 4 oxygens plus 1 is 5. So now we're at 5 oxygens. Okay. Now, how about hydrogens? Well, let's see. We got 2 of there. How if we put 3 here? That gives us 6 hydrogens. 6 hydrogens here. Right? That changes the oxygens to 4 plus 3 is 7, right? Okay, so we need 7 oxygens on this side. We've already got 1, right? So we really only need 6 out of this one. Okay, so if we put a 3 here, that makes 6 plus 1 is 7. And you can see at a glance that we're balanced. 2, 6, 7. That's my budget method. Now, what we've done we've stepped it up a little bit for the next one. This example.
You'll notice that the venue has changed. That's because we were interrupted in the middle of this lecture on campus. And this is my first opportunity to complete the lecture. So first thing I want to do is reshare the PowerPoints and get back to where we left off. And let's see, share, here we go. And let me turn that into a slideshow. Okay. Just in case, I'm not sure where we got cut off. It was in the middle of this slide. So I'm going to start over with this slide. And this particular equation that we want to balance obviously has to be written correctly. In other words, the ammonium phosphate must be written this way because ammonium has a +1 charge. Phosphate is a polyatomic with -3 charge. So we need 3 pluses to balance the phosphate's 3- charge. So that's written correctly. That's one of the prerequisites of balancing equations. All the compounds and elements must be written correctly. And sometimes it's important to put the state. In this case, AQ means aqueous. This compound is in aqueous solution. Calcium chloride is written correctly. Calcium is 2+ ion. It's an alkaline earth. And chlorine is a halogen with a -2. So calcium CaCl2 is correct. And then calcium phosphate is written correctly. It's a precipitate. This is a solid. We'll talk about those a little more later on. And then ammonium chloride is left in solution. Okay, so when we apply the budget method, notice that the ammonium is the same on both sides, right? There's no change in the ammonium. It's intact as a reactant and a product, so we can use it as a balancing group. Same thing for phosphate. It doesn't change during the reaction. Now, if these polyatomic ions get broken apart during the reaction, then we can't use this simplification. We have to use individual elements and balance the equation that way. But this is a method that allows you to save time and trouble if the polyatomic is intact for both reactant and product. Okay, so now we just bring in the first counting, an assessment of everything that we have both on the reactant side and the product side. Okay, now we're going to balance the calciums first. And some of this comes with experience. If you don't have enough experience to see patterns and which one would probably work best first, then use the suggestions in that handout I gave you. And since there are no simple element reactants or products, then we don't need to hold those out till the end. So you could start with ammonia, but in this case, I'm just going to start with calcium. So we're going to balance the calcium. We need 3 calcium on the reactant side to balance the product side. Okay, and that also changes the number of chlorines. All right, so first step, in those red letters, red numbers, that's the first step. Second step is assess the chlorines as well, because we did change the number of chlorines with that coefficient of 3. And then we're going to balance the chlorines on the other side. Since they were modified as a consequence of changing the coefficient of calcium chloride to 3, now we have to balance the chlorines on the product side. And that will take 6, a coefficient of 6, which will also change the ammonias. Right? And there we have the chlorines. There we go. So the chlorines are balanced. The calcium is balanced. We just messed up the ammonias. So we need 6 ammonias on the reactant side. And that's our next step. So a coefficient of 2 will balance the ammonias on the reactant side, and it will change the number of phosphates, which means we now have 2 phosphates on the reactant side. And as it turns out, that balances everything. So our equation is now balanced, and we can do something with it. This is the first thing that you have to do. Well, the first thing you have to do is write all the compounds correctly, then balance the equation. Then you can do stoichiometry, which is where we're headed next. This slide emphasizes the fact that a balanced equation, it only matters that the ratio of all the elements on both sides of the equation are the same. So we could say something like CaO plus C yields CaCe2 plus CO2. And I noticed that this calciums are correct. Carbon's not, because there are 3 carbons on the right and 2 oxygens. So once we get it balanced, we find that the simplest whole number ratio of coefficients is 2, 5, 2, and 1. But the same ratio could be accomplished with a 4, 10, 4, and 2. But we tend to prefer the simplest whole number ratio. So if we actually ended up with 4, 10, 4, and 2, we should simplify that by dividing the entire equation through with the number 2. And that would reduce it to 2, 5, 2, and 1. Right? Or we could divide it further, but we don't like fractional coefficients either unless we have to. Now in the future, if you stay with me in this course and the second course, you're going to find that fractional coefficients are permitted and sometimes preferred. But for now, we want the simplest whole number ratio for the coefficients that will balance the equation. All right. All right. Which of the following are true concerning balanced chemical equations? There may be more than one. The number of molecules is conserved. Is that true? No. Masses are conserved, yes. And numbers of atoms of each element are conserved on either side. So 1 is false. Coefficients tell you how much mass of each substance you have. False. Coefficients tell you how many moles of each reactant and product you have, or how many molecules you actually have. Atoms are neither created nor destroyed. That is true. 3 is true. Coefficients indicate the mass ratios. False. They indicate the mole ratios. The sum of the coefficients on the reactant side equals the sum of the coefficients on the product side. No. If it does, it's purely coincidental. Coefficients, the only thing the coefficients are doing is allowing us to balance the number of atoms of each element on the reactant and the product side so that they're the same. All right. That's what I just said right there in that first statement. Subscripts must not be changed to balance the equation. The subscripts are written in there to create a correct formula for the compounds. After that, once they're written correctly, you can't touch them. Subscripts are holy. They're sacred. Don't touch them. A balanced equation tells us the ratio of the number of molecules which react and are produced in chemical reaction. Yes, that is true. That's absolutely true. Coefficients can be fractions, but for now they should be given lowest integer multiples. That's true. The smallest whole number ratio of coefficients is preferred for the moment. Okay. Now, when we're going to do stoichiometric calculations, one What we're saying is that the balanced chemical equation can be used to relate masses of reactants and products. But we do not do it directly. We have to jump through some hoops. In other words, once the equation is balanced, and if we're given a mass of reactant, mass of one reactant, mass of another reactant, then in order to relate them, we have to convert those masses to moles. That's where the relationship occurs. If we stick with masses, then we're lost. We can't do it. It has to be moles. So I'm going to show you how to do that in just a minute. And the way we convert is by molar mass. Remember, when we calculated molar mass of the compounds, I wasn't just doing a fun exercise. That's absolutely essential. You have to be able to calculate molar masses of the compounds in order to convert masses into moles, so that then we can use the equation to relate it to other parts of the equation, right? So these are just steps that we follow in order to accomplish our stoichiometric calculations. Balance the equation. Any known masses of reactant or product, convert those to moles using their individual molar masses. Using the balanced equation to set up an appropriate mole ratio. That's one thing we haven't talked about yet. When you have a balanced equation, such as, well, let's see. Let's say we have sulfuric acid and sodium hydroxide, and that's going to yield sodium sulfate. We have to write a 2 there because this is a 2 minus, that's a +1, and water. Right? So we want to balance this equation. Right, we've got 2 sodiums here, we need 2 there. I'm going to do it without the budget method because it's really simple. And we have 2 OHs and 2 H2s gives us 2 waters. And then 1 sodium sulfate. So that's balanced. 1, 2, 1, 2. Here's what those coefficients are good for. If you know that you have 1 mole here, how many moles of sodium sulfate? No, better yet, how many moles of sodium hydroxide are required? Well, for every 1 mole here, you need 2 moles here. Right? So if you need to make a conversion from one to the other, say there's only 0.25 moles here. Okay, so 0.25 moles of sulfuric acid, and we want to convert that to see how many moles of sodium hydroxide are required. So our conversion factor is moles of sulfuric acid here. I should have put A there. Sulfuric acid here, and moles of sodium hydroxide here. That's a conversion factor. 1 of these, 2 of those. So 2 times that is 0.50 moles of sodium hydroxide are required for every 0.25 moles of sulfuric acid. So those coefficients can be used as conversion factors. Okay. Now, if you start off with a mass, then you want to convert to moles before you go to this step, right? Think of it this way. There's a great wall here. You cannot cross that wall with mass. The only way you can cross that wall is with moles. So if you've got mass here, you're stuck. If you convert to moles, then you can move to here or here or here. Okay? It's a barrier. It's a great barrier that you can't get around with mass. You must have moles. Okay. For those of you who like flow charts, you can pause the video and look at this stuff. All right. So here's an example. See if I'm still on camera. Yep, there we go. So consider this following a reaction, and it's already balanced for us. Right, so that's nice of them. P4 solid, that's phosphorus, plus 5 moles, 1 mole of P4 plus 5 moles of oxygen gas yields 2 moles of P2O5 solid. Okay. If you have 6.25 grams of phosphorus burned in air where there's plenty of it, right? Air doesn't restrict the course of the reaction. In other words, we will be able to consume all of the phosphorus. What mass of oxygen is actually required? Okay. So if we do this, say P4 plus 5O2 gas yields 2P2O5 solid. I think that's right. Yeah. Okay, here's the way I do this. I put the mass on one side and convert to moles and put that number on the other side, just to keep things straight. So we have 6.25 moles here, grams here, 6.25 grams. We want to convert that into moles. So what we need is a conversion factor that will cancel grams and leave us with moles. Whenever you see grams and moles in a quotient arrangement, right, a divisor arrangement, think molar mass. So if we see P4, so what's 4 times, let's see, I have to look it up. Phosphorus is 30.97. Grams per mole. So we've got 4 of them, right? So that's equal to what? Let me get out my calculator. 30.97 times 4 is 123.88. 123.88 grams per mole of that formula. So 123.88 divided into this, right, will give us the number of moles of P4. 6.25 and then divide by that number. And I get 5.045. So this is 5.045 times 10 to the minus 2. Yeah, moles. That's how many moles of P4 we have. Okay. All right. We want to convert that to moles of oxygen. And we use the coefficients as our conversion factors. Right. So we can take that. And this is 4. So P4 and O2 ratio. And I left out the moles because I'm short on space. But we have 5 of these for every one of those. So 5 times that value will give us the moles of oxygen. So that's 2.52 times 10 to the minus 1. Right? That's 2.52 times 10 to the minus 1 moles of O2. Now we can convert back to grams. So we had grams to moles, moles to moles, moles to grams. All right, so 2.52 times 10 to the minus 1 moles of O2. And then we use another conversion factor, which takes moles and leaves us with grams. Grams over moles is molar mass. So what's the molar mass of O2? Well, 1 oxygen is 16. So 2 of them is 32, obviously. All right, so we multiply that times 32. And that's 8.07 grams. that's how many grams of oxygen will perfectly combine with 6.25 grams of P4. Okay, there's the answer. I didn't have this one animated, so I had to do it on the board. All right, so now you get the gist. You go grams to moles, moles to moles, moles back to grams. This one is a little more complicated. This is a complex reaction, but if we break it down into pieces, you'll see that it's not that difficult. So let me make some room here. Oh, okay. So we've actually got two reactions going on here, but they are related by the question itself. Methane reacts with oxygen and air to produce carbon dioxide and water. Okay, that's one reaction. Ammonia reacts with oxygen and air to produce nitrogen monoxide and water. So it's two separate reactions. Write the balanced equations first. Okay, there's the balanced equation for methane. CH4, O2, carbon dioxide and water. And then we used our budget method and we determined that we needed 2 oxygen molecules. Remember, that's diatomic. 1 carbon dioxide and 2 waters. And if you want to verify that, all you have to do is say, all right, how many carbons are on the left? 1. Carbons on the right? 1. That's good. 4 hydrogens on the left, 4 hydrogens on the right. 4 oxygens on the left, 2 plus 2, 4 oxygen. So that's balanced, right? We confirmed it. Now ammonia reacts with oxygen. It's a little more complicated there. It might be useful to show you how that one is balanced. Let's do that. So if we have ammonia plus oxygen yields nitrogen monoxide, nitrogen monoxide plus water. Okay, so remember we do our, we have nitrogen, we have hydrogen, we have oxygen. That's it. 1 nitrogen here, 3 hydrogens, 2 oxygens, 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay. Now the question is, where do we start? Well, first of all, sometimes I like to check to be sure I counted right. Right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1 plus 3 is 4, 5, 6. 3, 4, 5, 6. Okay, so I counted right. We don't need to bother with the nitrogen right now because they're equal. How about hydrogen? Well, we do want to hold this one out till the end. Right? It's one of those tricks. If you find an element all by itself and a reactant or product, leave it alone. Don't touch it till the end. Okay, so that means we'll have to go to hydrogen. Well, hydrogen is the only one that's out of balance right now. So if we've got 3 on this side and 2 on that side, and they're in two, they're not in 2 places. They're in 1 place here, 1 place here. The easiest way to handle that is to cross multiply. So we would take this 2 and put it over here, and this 3 and put it over there. So that would give us 2 nitrogens, that's 6 hydrogens, and that would give us 6 hydrogens and 4 oxygens. Okay. Now, I think we need to balance the nitrogens, right? We need 2 nitrogens here. Okay. So that gives us 2 here. That gives us 2 plus 3 is 5 oxygens. Okay. Now, we've got oxygen in 1 place. This is going to show you one of those other tricks that are in that handout I gave you. helpful hints. When you've got an odd and an even, and there's only one place for it to occur, this is the last balancing coefficient we need. One way to do it is to use a fractional intermediate. So we need 5, but we got a doublet here. We got 2. So what if we do 5 halves? Okay, what's a half of an O2? Right, a half of an O2, right, is an O here and O here. So 1/2 of that gives you 1 O times 5 is 5 oxygens. That's exactly what we need. Okay, now we're balanced, but we got that fraction, right? So we need to get rid of the fraction. How do you do that? You multiply the entire equation through by the denominator of the fraction. Okay, that makes this 4, that makes that 5, that makes this 4, and that makes this 6. So 4, 5, 4, and 6 is where these came from. 4, 5, 4, and 6. That's a balanced equation. Okay. That took a little extra time, but it also illustrated some those useful, helpful hints when balancing equations. All right, so now we got our balanced equations. Now the question is, what mass of ammonia would produce the same amount of water as 1 gram of methane reacting with excess oxygen? Okay, so we got 1 gram of methane. The balanced equation, okay. Here we go. We got 1 gram of methane. We want to know what mass of ammonia will produce exactly the same amount of water for either one. Okay, so the connecting point is with water. So here's what we're going to try to do. We're going to say 1 gram of methane produces how many grams of water? Actually, we're going to make it simpler than that. How many moles of water are produced from 1 gram of methane? If we can find that out, then we know that the moles of water here is exactly the same as the moles of water here, and then we can go from moles back to moles of ammonia and convert that to grams. Okay, that's our plan. Okay, so the solution is going to be converting 1 gram of methane using its molar mass, many moles of methane, and then we use the coefficients to find out how many moles of water. So it turns out we have 0.1246 moles of water produced from 1 gram of methane. Well, that's exactly the same amount of moles of water that we want in this equation, right? So we take that many moles of water and convert that using the coefficients of 6 and 4, convert that to 8.31 times 10 to the minus 2 moles of methane. Now we can convert methane back to grams. Turns out that the same amount of water is produced by burning 1 gram of methane or 1.42 grams of ammonia. Okay. Now, topic of limiting reactants. Up to this point, when we did those reactions and we say burn some things in air, we were assuming that there was plenty of oxygen, right? No limitations. And that's true. It was true. But some reactants, some reactions have 2 or more reactants, and they're specified amounts of each one. Happens, you can be pretty sure that one of them is going to run out. Right? They are not in what we call a stoichiometric ratio. A stoichiometric ratio relates back to the coefficients in the balanced equation. That says that 1 mole of this and 2 moles of that will give you 3 moles of this. That's 100% conversion, and there are no limiting reactants. There's nothing going to run out. They all run out together. But in reality, when you're given amounts of each of the reactants, one of them is going to run out. And at that point, the reaction stops. And you have excess of one, and you have nothing left of the other one. So that's where we're going with this limiting reactant discussion. This just illustrates, if we take nitrogen and combine it with hydrogen to make ammonia, that's the Haber-Bosch process again. Well, maybe this is the first time we're exposed to that. This is the Haber-Bosch reaction. Notice that 3 moles of hydrogen combined with 1 mole of nitrogen. So there are 3 hydrogens, 1 there, 3 and 1, 3 and 1, 3 and 1, 3 and 1. This is a stoichiometric ratio because they all run out together and produce 2 moles of ammonia, 2 and 2 and 2 and 2. That's stoichiometric. In this case, the limiting reactant is hydrogen. Why? Because hydrogen is used up here, here, and here, and there's no hydrogen left over. But there are excess nitrogen molecules left over right here and here. We got this ammonia limited by hydrogen with excess nitrogen. Okay. So which of the following reaction mixtures could produce the greatest amount of product? Each involves the reaction symbolized by 2 hydrogens plus 1 oxygen yields 2 waters. Right? That's burning hydrogen in a rocket engine would be a good example. All right, 2 moles of hydrogen and 2 moles of oxygen. What will that produce? Well, one of them's going to run out, correct? 2 moles of hydrogen only needs 1 mole of oxygen, so it's excess, and the hydrogen runs out. Whoops, I gave you the answer. So that gives you, so A gives you 2 moles of water. B, 2 moles of oxygen. We still have excess oxygen. So that's another 2 moles of water. How about C? 2 moles of hydrogen and 1 mole of oxygen. That's stoichiometric. Exact ratio. That's the same. How about D? 3 moles of hydrogen and 1 mole of oxygen. Well, 1 mole of oxygen needs 2 moles of hydrogen. So 2 of these moles are used up with that 1 mole to give you 2 moles of water and 1 mole of hydrogen left over. Right? So it's the same. They all give you exactly the same amount of product. They just have different limiting and excess reactants in the process. So, okay, you can't just simply add the total moles of all the reactants to decide which one makes the most product. What you have to do is use the balanced equation to tell you which one runs out first. So we actually look at, one way to do it is to look at how much product can be formed by using what we are given. In other words, if we're given a certain amount of this reactant, say, what if it's all used up? Product will it produce? And then we take this one separately and say, if all of this one is used up, how much product will it produce? And you look at the one that gives you the least amount of product, that's the limiting one. Okay. We'll do more of those. There are review problems that are document I handed out today. But I need to get to percent yield now. Remember earlier on, I mentioned that the balanced equation is a representation of 100% efficiency. But as a matter of fact, the actual yield is always less than 100%. And to quantify that, we take the actual divided by the theoretical yield times 100, and that's the percent yield. Some reactions, I mean, you're lucky if you get 15% efficiency, and others you can get over 90%. Let's see. All right, excuse me, I messed up. Let me go back. Go back to this one. There we go. Okay, so we have this reaction. The phosphorus again, P4, only this time we're reacting it with fluoride, or the fluorine gas, and getting PF3 gas. And that's the balanced equation. The question is, what mass of P4 is needed to produce 85 grams of PF3, actual recovered amount, if the reaction is only 64.9% yield? So that's 64.9 grams of actual yield for 100 gram theoretical. The actual yield we want is 85 grams. So in order to use the balanced equation, we've got to work backwards. We got to find out what would be the theoretical yield if we were aiming for 85%. Right? So if we're aiming for 85%, 85 grams, excuse me, 85 grams, then what we need to do is divide by 0.649. Right? And that'll give us a value that then we can use in the equation. So I think that's what we're doing here. So I divided by 0.649 because it's 100 theoretical divided by 64.9 actual, and that's the same as this fraction. Okay, that means we need 130.97 grams theoretical to calculate the mass of P4 that we want to start with. Okay, so first we have to convert to moles, right? We can't move anywhere in that equation without moles. So we find the molar mass of PF3, convert to moles of PF3, then we use the stoichiometric ratio, 4:1, to find out that we actually need 0.3723 moles of P4, convert that back to grams, and that's what we need to start with. 46.1 grams of P4 will give us 85 grams of product with a 64.9% yield. Okay. All right. I mean, it looks complicated, but we break it down into pieces. We logically approach it. And with practice, it will become easier. I guarantee it. If you don't practice it, then it'll be a nightmare forever.